Inverse trig function. Inverse functions. If no horizontal line intersects the graph of f more than once, the function is one-to-one and has an inverse function. If the point AB is on the graph of f, then the point BA is on the graph of the inverse function, denoted f to the power of -1. The graph of an inverse function is a reflection of the graph of f about the line y equals x. So notice we have the sine function here. The inverse function, the horizontal line test shows that the sine function is not one-to-one. So y equals sine of x has an inverse function on a restricted domain from negative pi over 2 to pi over 2. So we're going to restrict it from negative pi over 2 to pi over 2. So basically we have just this piece of the graph. And then when I draw a horizontal line, notice that it will only intersect one time. So the inverse function denoted by sine inverse is the inverse of the restricted sine function y equals sine of x between negative pi over 2 and pi over 2, including. Thus, y equals sine inverse of x means sine of y equals x, where y is between negative pi over 2 and pi over 2, and x is in between -1 and 1. We read y equals this inverse sine at x. Graphing the inverse sine function, one way to graph y equals the inverse sine at x is to take the points on the graph of a restricted sine function and reverse the order of the coordinates. So notice that I have on the sine function, I have negative pi over 2 comma -1. If I invert this point, it becomes -1 negative pi over 2. 0, 0. If I interchange x and y, is still 0, 0. And pi over 2 comma 1, if I invert that, it's 1 comma pi over 2. And we're restricting the inverse from domain from -1 to 1 now, and the range is from negative pi over 2 to pi over 2 inclusive. Notice that the domain and range also swapped because we interchanged the points. Finding the exact value of sine inverse at x, we're going to let theta equal sine inverse at x. We're going to rewrite theta equals sine inverse of x as sine of theta equals x, where x is between negative pi over 2 inclusive to pi over 2 inclusive. And then we use the exact value in the table to find the values of theta that satisfies sine of theta equals x. You can also use the unit circle. If you're thinking about the unit circle, remember we're restricted from negative pi over 2 to pi over 2. So we're using basically these values between negative pi over 2 and pi over 2. Example 1, find y in each equation. We have that the inverse sine at 1/2. So we're going to let that equal y. So we can rewrite that sine of y equals 1/2. And now we're using the table or the unit circle. Where does sine of y equal 1/2? In other words, we're looking for the angle that it equals 1/2. Remember, this is the angle. And in this table is based on theta. Here I have the variable y, it doesn't matter. So where does sine of y equal 1/2? And our answers can only be between negative pi over 2 to pi over 2. And that occurs at pi over 6. So that means y is equal to pi over 6. Find y in each equation where inverse sine at -1. Once again, we're going to let that equal y. So that means sine of y equals -1. Well, where does sine of y equal -1? Y would have to be negative pi over 2. We cannot say 3 pi over 2. We can only use between negative pi over 2 and pi over 2. I understand that negative pi over 2 is in the same position or coterminal with 3 pi over 2, but you have to answer between negative pi over 2 to pi over 2. Find y in each equation such that y equals the inverse sine of negative square root of 3 over 2. Once again, we're going to say sine of y equals negative square root of 3 over 2. Look at the table. Where does the sign of y equal negative square root of 3 over 2, that occurs at negative pi over 3. Example 4, find y in each equation such that y equals the inverse sign at negative 1/2. Where does sine of y equal negative 1/2? And that occurs at y equals negative pi over 6. Inverse cosine function. So here I have the graph of y equals cosine of x. And notice if we draw a horizontal line test, shows that cosine function is not 1-to-1. But if we restrict it between 0 and pi, we restrict it just to this much, and I draw a horizontal line, notice that it will be 1-to-1. So the inverse cosine function, denoted by cosine of an inverse, is the inverse of a restricted cosine function such that y equals cosine of x and x is between 0 and pi inclusive. Thus, y equals the inverse cosine at x means cosine of y equals x, where y is between 0 and pi and x is between negative 1 and 1. One way to graph the inverse cosine of x is to take the points of the graph of the restricted cosine function and reverse the order. So notice the point 0, 1 becomes 1, 0, pi over 2, 0 becomes 0 pi over 2, and pi negative 1 becomes negative pi over 2. So our domain and range have swapped now. So finding the exact value of cosine inverse at x, we're going to let theta equal the inverse of cosine at x. We're going to rewrite theta equals cosine inverse at x as cosine of theta equals x, where theta is between 0 and pi. So once again, we can only answer between 0 and pi. So all our answers have to be between 0 and pi. In this case, you can use the unit circle, but the answers have to be between 0 and pi only, which is in quadrant 1 and 2. And we're going to use the exact values in the table or the unit circle to satisfy that cosine of theta equals x. So on example 5, I want to find theta such that cosine inverse at x equals square root of 3 over 2. So we have cosine of theta equals square root of 3 over 2. So here I'm looking at where does cosine of theta equal square root of 3 over 2? Well, that occurs at pi over 6. So theta is pi over 6. Okay, I don't have to use theta. I can use y. I can use anything to solve this. Once again, the next one I'm going to find the exact value where the inverse cosine equals negative square root of 3 over 2. So if we say theta equals the cosine inverse at negative square root of 2 over 2, then we have that cosine of theta equals negative square root of 2 over 2. And that occurs at 3 pi over 4. So theta is equal to 3 pi over 4. Once again, you can use the table or the unit circle. For the inverse tangent function, if I draw a horizontal line, test shows that tangent function is not 1-to-1, but if we restrict y equals tan of x has an inverse function at a restricted domain from negative pi over 2 to pi over 2. So once again, we're just using this right here. And if I draw a horizontal line, it will be 1-to-1. So the inverse tangent function has a restricted tangent function, y equals tan of x, and x is in between negative pi over 2 and pi over 2. And this time, notice it's not equal to. It's just strictly in the open interval. So y equals tan inverse of x means tan of y equals x, where y is between negative pi over 2 and pi over 2, and x is all real numbers. One way to graph it is, once again, to take the points and interchange x and y. So the point, notice the asymptote here is x equals negative pi over 2 and x equals pi over 2. Now it becomes y equals negative pi over 2 and y equals pi over 2. And then if I swap the points, negative pi over 4, negative 1 becomes negative 1, negative pi over 4. And pi over 4, 1 becomes 1 pi over 4. And the point 0, 0 is still 0, 0. Once again, the domain and range also interchange. So to find the exact value, we're going to say that theta equals the inverse tan at x. Rewrite it as tan of theta equals x, where theta is between negative pi over 2 and pi over 2. And then we use the exact value in the table or the unit circle. Once again, this time, my answers are in quadrant 4 and 1. But you have to use the negative angles in quadrant 4. And then in quadrant 1, it'll be the positive angles. You can use the unit circle or you can remember the table. So we have theta equals the inverse tan at square root of 3. Well, where does tan of theta equal square root of 3? Well, that occurs at pi over 3. Example 8, find the exact value of theta equals the inverse tan at negative 1. Where does tan of theta equal negative 1? Well, tan of theta equals negative 1 at negative pi over 4. So I've summarized the inverse properties for sine, cosine, and tangent in this chart here. Example 9, we're going to find the exact value of theta equals the inverse sine at sine of pi over 3. Now, you could use the properties or we could just work it by hand. So first of all, we're going to do the inside function first. We know that sine of pi over 3 is square root of 3 over 2. And now we need to figure out that sine of theta equals square root of 3 over 2. Well, where does sine of theta equal square root of 3 over 2? At pi over 3. Once again, you can use the properties or just work it from inside out. Example 10, we have that cosine of 2 pi over 3. Well, we know cosine of 2 pi over 3 cosine of 2 pi over 3 is negative 1/2. So theta equals the cosine inverse at negative 1/2. So then we have that cosine of theta equals negative 1/2. And we know that cosine of theta equals negative 1/2. So then theta has to be 2 pi over 3. Example 11, use a sketch to find the exact value of each expression. So first of all, we're going to substitute the inside function. So we have cosine of theta. So I'm letting theta equal the inverse sine of 1/5. So therefore we know that sine of theta equals 1/5. And I'm going to basically draw a triangle. We have that sine of theta is opposite over hypotenuse. So I can use the Pythagorean identity that says a squared. So I can use the Pythagorean identity and solve for a or b, whatever letter you want to call that. So I have a squared plus b squared equals c squared. So I have a squared plus 1 squared equals 5 squared. So a squared plus 1 equals 25. Subtracting 1 from both sides, a squared equals 24. And when I take the square root of both sides, it's plus or minus. So a equals, and 24 can be broken up into 4 times 6. So a is equal to plus or minus 2 square root of 6. Well, notice that we're in quadrant 1 for the inverse function because it's positive. Remember, inverse sine is only in quadrant 1 and 4. And here we have that it's the inverse sine of theta equals 1/5. So it's in quadrant 1. So a is 2 square root of 6. And now we're basically finding what cosine of theta is. So cosine of theta, because we substituted theta for inverse sine of 1/5. So cosine of theta is basically adjacent of theta, which is 2 square root of 6 over hypotenuse, which is 5. I'm using SOHCAHTOA to set up the triangle and then working it from there. Example 12, we're going to use a sketch to find the exact value. So once again, first I'm going to say that tan of theta is sine inverse at negative 3/5. So I'm going to set up that theta. I'm substituting that theta is sine inverse of negative 3/5. Remember, sine can only be in quadrant 1 and 4. In quadrant 1, it's positive. In quadrant 4, it's negative for the inverse function. So in this case, I'm in quadrant 4. So I'm going to set it up in quadrant 4. So we have that sine of theta equals negative 3/5. I'm setting this up in quadrant 4. Sine is opposite, which is negative 3 in this case, over hypotenuse, which is 5. And I'm going to look for this a. You can label it anyhow. I have a squared plus b squared equals c squared. We have a squared plus negative 3 squared equals c squared. A squared plus 9 equals 25. Subtracting 9, we have a squared equals 16. And when I take the square root, it's plus or minus, so a equals plus or minus 4. Well, here a is positive because we're in quadrant 4. And so now we have what we're looking for is tan of theta. So tan of theta is opposite of theta, which is negative 3, over the adjacent, which is 4. So here my answer is negative 3/4. Example 13, we're finding where tan of inverse cosine at x. Once again, this time x has to be positive. So we're in quadrant 1. And I'm going to let theta equal the inverse cosine of x. So cosine of theta equals x. And at the end, I'm going to look for what tan of theta is. That's what we're going to look for. That's our goal at the end. Because we're substituting inverse cosine at x for theta. So setting this up, I'm going to put a 1 underneath the x. So that way I have my ratio. Cosine of theta is adjacent over hypotenuse. And I need to find my length here. So we have... notice I'm just letting everything be a squared, what I'm looking for. You could do b, it doesn't matter. A squared plus b squared equals c squared. A squared plus x squared equals 1 squared. A squared plus x squared equals 1. Subtracting x squared from both sides, we have a squared equals 1 minus x squared. And then we're going to take the square root of both sides. Well, once again, when I take the square root of both sides, it's always plus or minus, but we're in quadrant 1. So a is equal to square root of 1 minus x squared. Note that you cannot take the square root of x squared and say that's x. That's not true, okay? So now we have that tan of theta is opposite. So opposite of theta is a, which was, we just found that by saying that square root of 1 minus x squared over adjacent, which is x. Example 14, we have cosine sine inverse at 1 over x. Once again, we're in quadrant 1 since inverse sine of 1 over x is positive. So I'm going to set up the triangle in quadrant 1. And we have that. This is going to be cosine of theta. We're going to let theta equals sine inverse of 1 over x. So now we have that sine of theta equals 1 over x. And sine of theta is equal to opposite. So we have, this is my angle theta, opposite of theta would be 1, and my hypotenuse is x. So I'm looking for this length, and this time I'll call it b. Like I said, it doesn't matter which one, how you label it, as long as you label it correctly. So we have a squared plus b squared equals c squared. So we have, in this case, 1 squared plus b squared equals my hypotenuse squared, which is in this case x squared. So 1 plus b squared equals x squared. Subtracting 1 from both sides, we have that b squared equals x squared minus 1 and taking the square root of both sides. Once again, it's always plus or minus, but in this case, we're in quadrant 1, so it's just going to be positive x squared minus 1. Do not take the square root of x squared and tell me it's x. That's not true. So we have b is equal to x squared minus 1. And we're looking for cosine of theta. Well, cosine of theta now is equal to adjacent, which is square root of x squared minus 1 over hypotenuse, which is x.